So first of all, so I'm Jay Lewis. I'm Deputy Director of MTO. First thing I want to say is just thanks for spending a little time to come hear about our office, MTO, Microsystems Technology Office. This will be the first of two sessions. They will be different. So we'll have another one tomorrow morning. So wanted to just start with a little bit of sort of an overview of the office. The fun thing about the next hour is you will not hear sort of a top-down strategy from me. You will hear from the program managers themselves. They are the ones who have the ideas, the visions, the dreams, the energy and motivation to make these things happen. And they'll talk a little bit about some of the things they're doing, and I think probably what you mainly want to hear, which is some of the ideas that are stirring around in their heads. And that will give you the chance to sort of talk to them early on. So just start a little bit, there we go. Quick overview of the office itself. So for those of you who are less familiar with MTO, we are, in terms of the overview of the agency, we're somewhat of a domain-specific office, so we focus on electronics. It's a very broad topic. Electronics really broadly as it applies to the Department of Defense. So what do electronics mean to the warfighter? One of the ways we like to describe it is this sort of image of the intersection between the physical world on the right. So this is air, land, sea, and space. Typical domains of battle in the electronics world, the digital world. On the left, so on the right, you would typically find our systems offices, TTO, STO systems, physical systems that orbit or fly or float. And on the left, you would see more of the programs from our I2O, Information Innovation Office. And MTO is really this seam. So typically, the things that you're doing in the digital world, you want to grab as much information or the right information from the physical world, bring that into the digital world. You need the processing capabilities to make decisions, and then have that influence your tactics. So in terms of the thrusts in the office, we typically describe them as three primary thrusts. The first one is electronics or managing Moore's inflection. So if you want to hear about the Electronics Resurgence Initiative, some of the computing programs, you are in the wrong place, or at least the wrong time. That will actually be tomorrow morning. So you'll be hearing from some of the PMs doing some of the computing programs. And what we'll talk about for the next hour are some of the work that we're doing in spectrum and sensors. So I'll go through very quickly how we sort of look at that space, but maybe do it through kind of the lens of our program managers. So we've been doing, the MTO has really been focusing on the RF spectrum since its inception. One of the real thrusts over the long term has been sort of the fundamental materials and device technologies to increase power, go to higher frequencies, higher bandwidths. That is still very much of interest to the office. We've really sort of moved into two different aspects of the RF spectrum. One is versatility. So just like physical fixed targets are easy to attack, the same is true in the spectrum. So we've been doing a lot of work to develop more agile, versatile RF systems. Tim Hancock comes from MIT Lincoln Labs, has been designing cutting-edge RF systems for DARPA programs, actually for a long time, and is now here with us in MTO, sort of thinking about how to make these sort of adaptive, agile RF systems. Once you have those adaptive RF systems, you still need to know what to do. So another aspect of our spectrum programs is intelligence and automation, and being able to make those decisions and to leverage that agility. Tom Rondeau comes to us from, he led the GNU radio project. So he's really spent most of his career thinking about this intersection of algorithms and mathematics and how you can use that to leverage the spectrum, so you'll hear more from him about that. As we go to higher and higher frequencies, we get to photonics. And so if you think about some of these advanced techniques that we've been developing for many, many decades in the RF spectrum, and you start to think about applying those techniques but leveraging optical frequencies, the implications are potentially incredibly profound. Gordon Keeler joined us from Sandia National Labs, where he's been working on integrated photonics for quite some time and is interested in sort of exploring what optical frequencies mean to the military technologies. So that's what sort of one or an array of optical sensors can do, but a picture is worth 1,000 words. And the balance of constraints is quite different if you're thinking about millions of optical sensors that have to fit into a diffraction limited pitch. That's what how we build our image sensors. And so Whitney Mason joins us from Army Night Vision Lab, and she is really thinking about the implications of advanced technology on how we can capture imagery in our sensor systems. Going beyond photonic frequencies to higher frequencies still, you get to things like electrons and atoms. And if you think about the most exquisite sensors you can imagine, you will probably very quickly get frustrated with the imperfections and the reproducibility of things that we build. So if you start thinking about atoms, nature has done us a favor. They all tend to be exactly alike. And John Burke comes from AFRL and has really spent his career building things like clocks and sensors that leverage atoms and quantum effects to explore sort of the boundaries of how we can sense our environment. Finally, we would like some of these microsystems to interact with the physical world. We're in a situation today where MEMS are becoming very advanced, but they typically have a pretty limited function, and they're a small part of a bigger system. We have bigger systems, mechanical systems, robotic systems that are much more complex, but don't scale down very well. And Ron Polkowicz comes from Army Research Labs and is really looking at how we can sort of blur that boundary between more sophisticated systems that are very, very small. And before I move on, I'll make one more announcement. Ben Griffin, if you could just stand up and wave for just a minute. So Ben's not on the chart. Ben will be joining MTO next month, early October. And Ben's background sort of started out in aerospace, sort of became more of a MEMS kind of a person, and is interested in a variety of things. We'll find out what he plans to do, but things like electronics in very challenging environments are the kind of things that I think Ben will be thinking about. So won't get to hear him talk today, but now you can put the face with the name a month from now. So with that, we'll get to the good part, hear from the PMs themselves. So why don't we start with Tim? Come on up.
Great. Thank you, Jay. So let me start with just a little bit of background about myself. Jay mentioned I'm on loan from MIT Lincoln Laboratory. My background is RF integrated circuit design, but I've also used COTS components, built some MIMO communication systems, as well as worked in the area of some device development, specifically GaN and some CMOS work. So with that, I'm going to start by telling you a little bit about my latest program, and that's millimeter wave digital arrays, or MIDAS. So to frame this, especially since this is D60, let's talk a little bit about the last 60 years worth of phased array development. It's intimately intertwined with DARPA's investments. And you can see along the y-axis, let me frame this in terms of sort of how hard it is to build a phased array. At lower frequencies, the pitch of the antenna elements are on the order of maybe a foot. But of course, as we go up in frequency, they become on the order of a millimeter for millimeter wave. What we've seen over time is a progression from passive beamforming to active analog beamforming, and eventually digital beamforming. So what you can see is in the lighter blue are advancements that DARPA has helped invest in. Things like the MIMIC program or the TEAM program, things like DAHI and Elastics. We've invested a lot in silicon, compound semiconductors, and packaging, and that's allowed us to move up in frequency. And so that's done a couple things for us. It's allowed us to put phased arrays on platforms that we couldn't in the beginning. Instead of having just fixed installations as we did early on, as electronics matured, we were able to put those onto ships, onto airborne platforms, and now we're even putting them onto smaller emerging platforms. But something has happened in the last 10 years, and that is digital beamforming has really come of age. We see this as an example, the space fence. This is some technology that's coming online here very soon. If you aren't familiar with space fence, that is an element-level digital array that is the size of about a basketball court. And that's in the Kwajalein atolls in the South Pacific for monitoring debris and stuff like that in space. This has really been enabled partially by COTS electronics and the advent of using GaN, since this is a high-power radar. As you may be familiar, the ACT program has really pushed forward on element-level digital beamforming. That wasn't exactly its intent. The intent was to push on to develop a common module. It turns out, though, that the best way to develop a common module was to actually go digital and remove some of those exquisite analog electronics that we have to redesign every time. Unfortunately, some of the work there in ACT really won't scale up in frequency. We need to be able to figure out how to reduce its power consumption and make it all fit behind something that is no longer about a centimeter, but something that is on the order of a millimeter. And that's really what Midas is focused on. So we'll be leveraging our past work in devices, circuit design, and packaging to go about and figure out how to do this. Why do we even care about millimeter wave? Well, we care about it because we like it for communications applications. It's inherently physically secure due to the narrow beams. We enjoy this today on our most exquisite platforms. It's difficult and hard to use because we have to figure out how to point them. And so that's why we reserve them for our most exquisite platforms. Shown on the screen is an example of what we put into the F-22 and the F-35. This is the iFiddle link and the Mattel link. And so because this is so hard, this is why we think we need Midas to be able to help us do that. And so under the program, one of the things that we want to be able to do is multi-beam network communications. And so having multiple simultaneous beams will help simplify the network discovery and how we do handoffs and things of that nature. Additionally, Midas will focus on wideband and frequency agility. This gives us the freedom to operate with impunity within the millimeter wave spectrum. So there'll be two core digital areas within Midas. That is to develop a digital tile in silicon CMOS that covers the 18 to 50 gigahertz band and provide a couple gigahertz of instantaneous bandwidth. Additionally, we have to figure out how to integrate that piece of CMOS with the higher power compound semiconductors and the wideband antenna components. And that's the other core technical area, so that at the end of the program, we really do have a tile building block that we'll be able to use to cover 18 to 50 gigahertz band. This will be useful for our line of sight tactical communications, as well as traditional SATCOM to geosynchronous orbit, but also some of the emerging LEO SATCOM that will be coming online over the course of the next decade. So with that, you might be asking, well, what is next? What else are you planning to work on? Well, in the near term, I think we need to fill some of the gaps between the antenna and the common module. We now have wideband antennas, we have wideband amplifiers, and we have wideband transceivers. Things that we still struggle with, though, are wideband reconfigurable antennas. We still struggle with things that we want to put into a phased array is simultaneous transmit and receive. That's a very challenging problem to do at the element level within a phased array. Additionally, wideband power and efficiency is also something that we're very interested in, and these are places that I've already started to make some investments. Further out, what else do we need to work on? I think some remotely powered energy harvesting. We need to work on something about flies, apparently. There's the remotely powered energy harvesting RF microsystems. So imagine a cloud of dust that you could power remotely, and it could do remote sensing for you. This is going to require low power RF microsystems, energy harvesting, and they're likely going to need to collaborate with each other and do that with very limited processing and very limited communications between them. Beyond that, those are sort of system level interests. Beyond that, there are always component level interests that I have. Some of those are close-in phase noise reduction for microwave and millimeter wave radar. This has always been a challenge, as you can imagine, when you consider the phase noise and how that affects radar. That's an important area of research in that sort of 1 to 10 kilohertz offset range is important. And then beyond that, I would say revolutionary materials and devices for RF applications. Things that come to mind, I think we'll probably see in some of these near-term interests, things like maybe multiferroics might show up for some of the filter work. But also, people have asked if anybody went to the wide bandgap semiconductor session yesterday, well, what's after GaN? GaN has an immense amount of legs left in it. I'm not worried about GaN going away anytime soon. But it is fair to ask, well, what is next? Should we be investing in the next technology that might happen in the next 20, 25 years? So those are all things that I'm interested in. So I encourage you to come talk to me. And I'd be happy to talk to you about any of these topics. So with that, I will hand it off to Tom for something completely different.
Yeah, thank you, everybody. So I'm Tom Rondeau. As Jay said, I came from the GNU Radio project. So this is a free and open source software radio platform that we've been working on for almost a couple of decades now. What it is it enables us on our desktops to do software-defined radio, or software radio, as I like to just call it. And software radio is an incredibly cool and incredibly powerful concept, and I'm going to tell you about that later. First, I want to talk about information, and why information is a cornerstone to everything that we do here. So information is the representation or quantification of information as the bit. So when we move bits around the world, as a radio guy, I get super excited about this because we move bits, we move information through the electromagnetic force. It's a really cool concept, but what I've realized in talking about this is that very few people care about the action of moving a bit from point A to point B. Think about your drive here today. You probably didn't think about the road you were on. You just thought about what was going to happen and all the cool things you were going to hear when you got here. You don't think when you open up the D60 app, the base station or the Wi-Fi access point that got you that information. You just care what happens when you look at that. And that's totally fair. But we think about it in terms of how we actually get that information to you, how we actually use the infrastructure to move information around. You think about us when those things fail, when your bridges fail, when your cell phone fails. So information is key, and what's really cool is this idea that we can quantify and mathematically represent information. So that was given to us by Claude Shannon in his paper, Mathematical Theory of Communications. And so that brings me to the video that I have playing behind me and probably distracting you. This was a film made by the artistic couple Charles and Ray Ames, so the famous Ames lounge chair. They were asked in 1953 to produce a film by IBM, to produce a film to explain to their employees, to their customers, and frankly to the world, the concept of information theory. So 1953, this is 5 years after Claude Shannon published his paper, which is maybe one of the most powerful and influential papers ever, at least of the 20th century. So they do an incredible job of explaining information theory here, and I hope you go and watch this. It's on archive.org to see how they look at this. Because while Claude Shannon was interested in how we use the electromagnetic force to communicate information and how to mathematically quantify that, they take a separate, another tack on that, where they look at information just as any medium of transmitting an idea from a transmitter to a receiver. They're artists. Their artwork is a transmission of their idea. We are the receivers of that idea, and we perceive that in some way. We see it, we hear it, sometimes we smell it. Artwork is perceived by our senses, And what I like about this is perception is the combination of the sensors itself, the eye, and the processing of the brain. So those two ideas together are perception. And we don't separate those two. We don't think about our eyes as completely independent of our brains. They work together in concert to allow that perception to happen, to extract information and what we perceive from what we see. So that brings me back to software-defined radio. Software-defined radio, or software radio, is the combination of the processing and the perception, and the reception and the processing to perceive those radio waves. So we know from Turing and Gödel how to build computers that can compute most of mathematics. We know from Shannon how to represent mathematically communications. So let's put those two things together. That's what software radio is talking about, is bringing the radio into the computer, intimately tied to the processor so that the processing and the sensor, or the actuator, are actually working together. This is a really cool concept because in GNU Radio, say, we were able to bring the radio directly into the desktop. So what I'm telling you here is that software radio is the ability to program the electromagnetic spectrum. I can write a Python script that can manipulate the electromagnetic waves, one of the 4 fundamental forces of the universe. And we do that through code. So that's what I'm here for at DARPA, is to really expand that idea, push those ideas out there for national security, for national defense. So what do I care about? There's 3 things that I'm interested in at DARPA. The first is better access to radio waves. There's a cool idea that I like to think about called, how do I make spectrum fungible? But I just want access to whatever spectrum that I can have, pull it into my system, process that. And we're working on that. You heard Tim looking at those ideas for millimeter wave. We've looked at them in ACT and my program Hedgehog for the lower bands. So that's kind of in process. We're still interested in better ways to do that, more innovative ways to get access to spectrum. The second thing, though, that I'm interested in is if I'm going to pull these things closer together, if I'm going to tie them intimately together with the processing and the sensor, then I need a better processor. So all the mathematics, even though I know I can compute all the math that I want to do for those radio waves, I quickly run out of processor power in which to compute them. So we're looking at new ways of computing, new ways of representing data, new ways of representing information. And specifically microsystems that look at this from a hardware-software co-design. So thinking about it from the whole system of what are we trying to solve in software radio, how are we going to compute that? That's the fundamental work that we're looking at in my program, the Domain-Specific System on Chip, or DSSoC. So we're pushing on that flow as well. So we've got those programs out there. Always interested to hear more, better ideas for how to use these systems, where they should go, who can benefit from them. The third thing is what I really would like to get more ideas on. This is, if I have the ability to access all the spectrum, if I can compute all these ideas, what am I going to compute? Information to the warfighter is one of the most fundamental aspects of the maneuverable battlefield today. Transmitting information, receiving information, processing that information, trusting that information are keys to the warfighter. We need to be able to respect that, to control that for our warfighter, and we need to deny the adversary the ability to do the same thing. The keys to electromagnetic maneuver warfare are in the ability to quickly manipulate the complexity of the electromagnetic spectrum so that we can have full control over those bits and their representation of information to us and against our adversaries. So those are the ideas that we're looking at as to how to enable the microsystems devices that we're building to interface in the electromagnetic spectrum and the information processing domain that's going to take us to that next level. And with that, thank you.
Thanks. All right, good afternoon, everybody. My name is Gordon Keeler. I'm going to switch gears again. I'm going to talk about optics. And I'm going to give you a little bit of the past, present, and future of optics at DARPA. A little bit about myself. So I grew up My dad was a physicist. What I loved from when I was really young was optics and lasers. And before I hit high school, I had made my own laser in his lab. And in high school, I was doing spectroscopy. Since then, I had my own optics lab, which was sort of a dream. And I left that last year to come to DARPA. So now I'm doing all of this through everybody else's hands. I'm going to tell you a little bit about some of the things that some of my great performers are doing and some of the directions I want to go. Okay, so this story is really about photonics, which is where optics and electronics meets. And so really, the story is about light. Right? Light is pervasive, touches all of us every day, used for information transfer, the internet, energy. And so thinking about the past, I decided, okay, let's look at how really briefly, mankind has tried to harness light, because really that's what we're doing in MTO, okay? Step back, way back, look at some milestones, right? We started with fire, use it for heating, cooking. We came to electricity, so we can turn on photons at the flick of a switch, and this really led to a revolution in productivity. 1960, the laser is invented, and this is the first time we can really, really control light. Control the direction, control the color, the frequency, polarization, and phase. 2 years later, the semiconductor laser was invented, and that's really where photonics starts to take off. Right? So we've got light now in the form of a chip, and you can put it everywhere. And so you can use it in lots of ways that you couldn't before. Right? You can put it in laser pointers. You can put it in your cell phone. You can put it on sharks. You can put it pretty much anywhere, right? And so one of the things I want to do is think about where we can use it sort of for good and for things that the DoD cares about. So these pictures are some of the things that I was doing at Sandia before I came. And again, it kind of talks about the whole different space that we can use photonics. Not necessarily all integrated photonics, maybe optoelectronics integrated into microsystems. I'm really interested in how we use it in information, digital communications, maybe for computing, maybe analog, maybe quantum. For vision, both for imaging and for displays. Microsensors, there's a lot we can do here, a lot of things we are doing now to do chem, biodetection, position and timing. And then control of energy, harvesting energy, directing energy, controlling our emission patterns. If you've got ideas in any of these, in optical microsystems, let me know. I know it's a big range of things. So looking at what we're doing now, I'm going to go back to the harnessing light. And really, the programs that I have now, I'm fortunate to have some really exciting things to work on. And I'm going to give you a little taste of what DARPA is doing, what MTO is doing, about trying to harness and control light. I think it's very exciting. MOAB, Modular Optical Aperture Building Blocks program, is looking to shrink LiDAR systems to the size of a chip. So typically, LiDAR systems, Velodyne sensors perhaps, fantastic, exquisite systems that are used to do autonomous navigation, or bigger systems used for surveillance. These systems, though, are generally optomechanical and big, bulky, and costly. And so MOAB is looking to create optical phased arrays, similar to what Tim was talking about with RF, but much, much smaller yet. And so using thousands and thousands of elements, putting them on a chip to control light beams in space with no lenses, with no moving parts. And so that allows you to think of something that's extremely small and put it everywhere. That's the idea, putting LiDAR everywhere. If you can control beams in space, then you can actually use it for lots of other things. So I'm interested in that as well. Looking quickly, we've got a demo downstairs if you're interested in seeing this. But we now have unprecedented spatial control of light. Another program, DODOS, Direct Optical, Digital Optical, On-Chip Optical Synthesizer. This is unprecedented control of frequency or wavelength of light. And so essentially a new area of optical physics is optical frequency combs. DODOS is looking at translating stable RF tones up to optical frequencies. And we've recently had great success on this program, Nature papers and fantastic control in systems the size of a sugar cube. There are a lot of applications for this that are sort of on the horizon in terms of communications, optical sensing, and interfacing with atomic systems. So where are we going next? There's a couple things that I'm going to talk really briefly about. One is wrapped into ERI, really, and it is looking at the way we communicate in microelectronic systems. Larger systems, we're using optics everywhere for the internet, in data centers, HPC. But at smaller systems, these are all microelectronics. And Moore's Law has successfully allowed us to pack more and more transistors into a package, but Moore's Law doesn't help with signaling. And so photonics, because of a lot of investments from DARPA and elsewhere, has really become much more manufacturable than it had been even a couple years ago. And so we're at the point where we can start to think about realizing this vision that people have had for a long time of truly putting photonics into a package. And I think that's where we're going next. So if you've got ideas, come talk to me. I think it'll have broad applications for the DoD and beyond. And it's really driven by parallelism. But also next, what else am I interested in doing? I'm interested in bringing photonics technology forward, not just for datacom, but for sensors and things that the DoD cares about. Again, this investment in silicon has given us a very manufacturable platform. It allows you to have photonics really small, low swap, low cost, and put it everywhere. But in fact, it's not good enough yet for a lot of the things we want to do. Some of the things that we want are gain on silicon beyond where we've got today. Gain at visible wavelengths and mid and long wave IR perhaps. Silicon has very weak effects, a lot of loss generally, and is missing key functions. And so what I'd like to do is look at bringing new materials to the platform, reducing optical losses, and looking at nanophotonics, so much tighter optical confinement to enable a lot of these new capabilities. So the idea there is essentially integrated photonics on silicon platforms, but getting rid of a lot of the silicon that we use today. So efficient on-chip gain, wide spectrum operation, ultra-wideband compact footprint devices, and looking at nonlinearities, non-reciprocity, and reconfigurable photonics. Thanks very much.
Hi, I'm Whitney Mason. Before I came to DARPA, I was 18 years at Army Night Vision and Electronic Sensors Directorate, mostly in the Science and Technology Division, doing a lot of work on infrared focal point arrays, in particular long-wave infrared focal point arrays. And what I want to work on while I am at DARPA is making sure that we never again waste an aperture on a focal point array that can only do one thing. So it's all about multifunctionality for me. So I was really lucky when I got to DARPA to inherit the Reimagine program, Reconfigurable Imaging. And it addresses part of this problem. So what you see on the left is a sort of traditional system. The pink material is your absorbing material. Merck had strain layer, superlattices, whatever. The tier beneath it is the readout integrated circuit, and everything comes off and goes to some FPGA or some sort of ASIC or something for processing that goes on to the computer or the display or something else. What Reimagine does is it takes part of those resources out of the FPGA, integrates something that looks very similar to an array in the middle of it, and 3D integrates it to the bottom of your focal point array. What does it do with it? Well, it's super exciting. It acts like a controller, first of all. Basically tells regions of pixels what sort of measurement they need to take now. So one of the first things that you can do is you can do binning in a two-dimensional sense. Now you might think to yourself, I can already do that, right? But what we do now is like a checkerboard. Using Reimagine, you can get something more like a mosaic that Tim Grayson talked about yesterday, where you have more information where you need it and less information where you don't. Because information you don't need is really just noise. The second thing you can do is you can add a laser and some gating, and you can get 3D information. The third thing you can do is you can change the frame rate. Now the picture on the bottom, we've seen pictures like this before. They do this at the Olympics, right? Where they turn on really high-speed cameras and you can pull out the information high speed. But what's different in Reimagine is each one of those windows could be a different frame rate. And in fact, each of those windows could be a pretty high frame rate, some up to hundreds of kilohertz. What does that mean? It means that you can pull in temporal capability. So What you see here on the right is a bee flapping its wings. It's taken at 70,000 frames per second. And using some of the processing capability that's around the Reimagine chip, you can do a fast Fourier transform and pull out its characteristic frequency. Just of interest, bees happen to flap their wings at about 250 hertz. So in the video, you would see something moving. You would know there was something there, but using this capability, you could actually pull out an ID, a signature, and know what it was. So what's next? Well, so now we can reconfigure spatially. We can reconfigure temporally. The last frontier, of course, is spectral. So there's two aspects to this in my mind. First of all, you have to have the hardware to be able to inject spectral information in. And the second thing is you need software to decide which colors to inject in. This is not hyperspectral. You should not think of this as a hyperspectral system, because a hyperspectral system only does one thing as well. This is the judicious addition of spectral information where it's needed. Or subtracted, for that matter. Think degraded visual environments where you need to subtract some of the information. Think sunlight where you need to not see that. If you look at this picture on the left and focus on the man that's walking into the building over there, when he goes into the shadows, you lose him, right? With the simple addition of infrared imaging, you would be able to pull out that man forever. If you look over here on the right, in the picture in the inset, that's an infrared picture. You can see that there's smoke, but is it good? Is it bad? I don't know. With the judicious addition of spectral information, you can tell what the chemical composition of that material is. So what would you do with this? Well, this is a cartoon, obviously. On the right is gray, but you can think of this as the temperature difference between the sky and the ground. And you can clearly see that there's a line. The colors just make it a little bit more clear. Still a cartoon, but much more realistic, right? Cameras have noise in them. Now tell me where that line is. Well, you're going to speculate that it's somewhere in the middle there, but you're not going to land your helicopter based on the information that you have there. Color certainly pulls out the information much better. Really and truly, what the helicopter pilot probably wants to see is something that looks closer to this. On the left is a long-wave infrared picture. On the right is a colorized picture of the same image where the color is applied as a function of temperature. It's a kind of thermography picture. And you can see, I mean, I would argue that that picture on the left is gorgeous, but there's not enough information. The picture on the right provides key information that the soldier, the warfighter, is going to need in order to be able to do his job. Now, a hyperspectral system could do this, right? Eventually. Could scan across the scene. And if you're only looking for one signature, it could give you the signature pretty fast. But if you had to colorize this entire image, it would take a long time. And the reality is the pilot wants to land right now. Coming back to Reimagine, I showed in that first picture, I took an FPGA and I stuck it on the bottom of my focal point array. And there's a lot of people that are going to make the argument that that's a really bad idea because I just added power to this. But I'm going to make the argument that it's not the power that's the problem, because I just took the power from one place and put it someplace else. The problem is that I put it in a 77 Kelvin operating temperature door, and now I have to have a bigger cooler and I have to get rid of that heat. Don't get rid of the FPGA, don't get rid of the material, make it operate at higher operating temperature. So DARPA and others have done significant amounts of work to change operating temperature of midwave material from 80 Kelvin to 130 Kelvin. I think it's time for another leap. I think that we need to have 240 Kelvin operating temperature. You can make this up with Reimagine, and it'll work beautifully with added capability without the bigger cooler and the heat dissipation problem. And this is for midwave, say 5 microns or less, particularly if you want to think about APDs where your power draw is going to be significantly higher. Also might be time to think about coolers again. Now for something completely different. The greatest thing about being at DARPA is that you get to be surrounded by brilliant people. And there's just these ideas that just float around and there's new things coming in that you get to hear about all the time. So sitting at the ERI and hearing about all the stuff that's going on and talking to my colleagues, it occurred to me that it might be time to think about chip scale mass spectrometry again. There's lots of work in mass spec. So what is the space here? There's exquisite systems with extremely high sensitivity that sit in a lab. They're high size, weight, power, and cost. And then there's portable systems that don't provide a great deal of sensitivity. Want to change that paradigm? I want to put a cute little sensor on a UAV, send it out with exquisite performance so you can get user feedback and real-time user information in real time. If you have ideas about this or anything else that I've talked about, please come talk to me. Thank you.
Thanks. So I'm John Burke. I'm, as was said, from Air Force Research Lab, and spent my career thinking about atomic physics, and in particular, how to take atomic physics experiments that are very elaborate and eloquent in the lab and make them into useful things for the military and for society as a whole. So I couldn't help but think about some of the past of so-called quantum technology, where I'm thinking about atomic physics mostly. So I think about some of the first technology from quantum put into the DoD, thinking only back to DARPA at the very beginning, thinking about the space race, sort of the first technology bridge that DARPA was, it stood up and met the need for, of answering Sputnik and putting, and getting us to the point where we have space superiority, and GPS in particular I'm going to focus on. So you might think, well, that's a wonderful story, but quantum was there that whole time. 30 years before the space race even started, we started thinking about this. Quantum theorists were busy at work trying to think about how to explain how atoms and eventually photons worked. And so one of the first quantum technologies is the cesium clock made by Essen in 1955, a couple of years before Sputnik was launched and surprised us all. And from there, the HP 5060A was the first, one of the first commercial quantum technologies, an atomic clock, which was quickly realized could be useful if put into space to make a radio navigation network. So the role of quantum goes all the way back to the very beginning of some of the things that DARPA was doing. So today, fast forwarding quite a ways, one of the next key pieces of quantum technology, I think, is the laser. You've already heard a little bit about that. I'm going to highlight here the gallium arsenide laser that eventually made it into CD players. If you were in the 90s, you remember all of your music came from CDs. Well, there's no accident that that same laser developed for CD players was put to work in one of the first laser-based atomic clocks, the CSAC, the chip-scale atomic clock that MTO led the charge in producing. That's pretty recent. So now we've built another bridge using lasers and atoms working together. And that was just the beginning of, I think, this sort of new era of atomic physics 2.0, I'm calling it here. While we were developing in the military the chip-scale atomic clock, the physicists in the lab were working on a whole bunch of new technologies, bringing lasers and atoms together to do very elaborate things. And so now it's kind of a point where we're thinking about building yet another bridge, a much more elegant bridge to get around some of the limitations we already face. So things like that were invented were things like laser cooling, trapping of atoms, frequency combs to link RF and optical frequencies together. All those things were laser-based and won Nobel Prizes for folks that developing them. Also, just a brief mention, the C-Naught gate for ions. This is one of the first concepts that gave us the hope that a quantum computer could really be built someday. All over that time, clocks got 1,000,000 times better in the lab, really leveraging all of this laser and atomic technology put together. So the thinking now is we knew that atomic physics led to great gains in the space race via GPS and other space technologies as well. So I'm keenly interested in how these might impact sort of, I'll call it Space 2.0. And you heard a little bit about this earlier today or yesterday, thinking about what we need to do in space to make it more reliable going into the future. Well, quantum technology may play a role here again, clocks especially, and so I'm particularly interested in trying to figure out a way to leverage that. So here's sort of a map of current programs I'm managing. So quantum sensors, atomic-based sensors are pretty useful at measuring the fundamental forces. So I've got kind of on the left timing, inertial forces like gravity, magnetic and electric fields. So I have these three programs, ACES, Atomic Clock of Enhanced Stability. This is a clock leveraging part of that Atomic Physics 2.0 to make better atomic clocks for ideas in communications and also thinking about navigation. Time being one of the 4 variables when you're trying to get a fix of where you are, X, Y, Z, and T. Of course, leveraged correctly, you can form the full position of where you are. So, for example, in GPS. So thinking about how to leverage ACES for navigation is a key interest of mine. But beyond that, we have the new program, AFI. There's a BAA out in the street now, so you should go read that BAA and think about how to solve problems presented there. That's really focusing on inertial technology and also timing, trying to capture the other factor of 1,000 left on the table for making very good atomic clocks and trying to figure out how to make them useful outside of the lab. Again, thinking about navigation directly, but also starting to think about distributed sensing, of how we can use clocks to coordinate different sensors across a large geographic region, perhaps. We have a magnetometer program called Ambient that's really focused on bioimaging. You heard a little bit about the human-machine interface, the brain-machine interface. Well, magnetic fields are a key mechanism for seeing what's going on in the brain, and Ambient is thinking about how to see those brain signals more easily. Also, many objects have magnetic fields that you can see, so Ambient, we're thinking about remote detection concepts as well. So there's not an electric field program, but I'm starting to think about that too. People have postulated several kinds and done several experiments in electric field sensing, so thinking about how to leverage that for a DoD application is also a key interest of mine. So one key thing here is trying to use atoms and the exquisite sensitivity they provide to map these sort of fundamental sensors into key applications. So if you're coming to me because you're interested in how to make a better electric field sensor, I'm going to ask you how do we use that for a real application. So we need to have that conversation, so keep that in mind. Okay, and I had to at least mention the sort of most far out quantum technology, the quantum computer. We don't really know what the first useful quantum computer might look like, but I will say that these different atomic physics-based quantum sensors were developing the techniques, metrology, and so on that may be important for those quantum computers in the future, depending on how exactly they come together. So with that in mind, I am thinking a little bit about quantum computing, so happy to take interest from you from that. But again, remembering that we want to have a path to get there, and there's a lot of challenges to think through there. So here's sort of a laundry list now of these atomic physics-based devices. Don't exist on their own. They're sort of little miniature systems and systems, so they require a lot of components, not just lasers, but also different other active photonics components. So I've got kind of a list there of particularly interesting devices. Particularly, I'm interested in applications of precise timing. I've kind of mentioned that, especially for space, but also for different communications protocols. If you have a situation where both you and I share a common timing reference we can rely on, there might be some interesting communications ideas we could use to leverage that. So interested in that. Distributed sensing also. Clocks are only so useful as you can connect them, so time transfer is a key interest also. A variety of other kinds of sensing modalities, tunnel detection in particular, we're starting to look at a little bit. I mentioned electric field detectors. I also mentioned kind of speculative atomtronics. Well, this is sort of a nascent field that's been around for a few decades. The idea of storing classical information inside atoms or other quantum objects. Just thinking a little bit through that. This is a little farther term and a little less knowledge about what we want to do there. And I mentioned quantum computing again. With that, I'll thank you. Pass it on to Ron.
Oops. All right, thank you, everyone. So I'm Ron Polkowicz. I've had the pleasure of coming to DARPA about just over a year ago. And I'll talk to you a little bit about my background and some of the programs of interest. So I was at the Army Research Lab prior to coming to DARPA for 18 years, leveraged a background in piezoelectric thin films to develop basically a 150 millimeter process line with PZT thin film capabilities at ARL, doing a whole host of things with actuator technologies, looking at RF systems, digital logic systems, all the way to millimeter scale robotic systems. And that'll be a theme you kind of see later on throughout the presentation. So one of the things I had the pleasure of taking over as a program was the Precise Robust Inertial Guidance for Munitions program, or the PRIME program. Something I tracked as part of ARL originally, worked with the previous program manager and had the pleasure over the last year kind of to push this program forward. This program is split between two active areas, right? So one is the Navgrade IMU, or NGIMU aspect, where we're trying to take something about the size of a small basketball into a hockey puck size for navigation grade performance IMU for high G environment. Munitions and missile systems. The second aspect is more of a 6162 research effort, looking at what is that technology that's needed to really push the technology beyond Navgrade environment, as well as high dynamic range of operation. So can you push 50,000 G operational stability for some of these inertial sensors? So as we move forward into this program into phase 3, we're looking at those transition opportunities for the NGIMU effort with our mission system side of things, as well as looking what are those opportunities for some of those more promising technologies that are coming out of the Ames program, and what are those what is the follow-on efforts that look like for an IMU, taking some of those best case inertial sensors. Next program, this is one of the programs I came to DARPA to initiate. So this is a BA that's out there on the street right now, end of September. The due date, we'll talk, sort of high level goal, how do we develop the technologies to enable untethered microrobotic platforms? If you take a look at what the existing activities in the university and academic research fields are, most of those technologies are highly limited by actuation and power. And so our first two technical areas try to address those challenges in both actuator materials and mechanisms, and then power conversion and power efficiency. And then the last one is TA3, where we really try to bring everything together to enable that fully untethered microrobotic platforms. And in the unique thing in phase 3 of that program is how do we bring those efforts together to really showcase the capabilities of those in these Olympic-themed events between like rock piling, steeplechase, biathlon, and a vertical ascent capability. So a couple other things that I want to transition into. Where am I thinking about? Where are we going? This is a workshop that we held in May of this year to really look at within the MEMS space, where we have a lot of production capability of devices in your cell phones, the DoD is accessing in various different platforms. How do we open up those access points? So my inspiration for this was, if I go back to things we heard yesterday in one of the sessions where you say, well, the genesis of VSI and MOSIS to really open up that door space for low volume production in the S&T community to access some of those more mature technology spaces. Is there something equivalent in the MEMS space similar to what we've done in the integrated circuit space? And so we brought together a whole host of folks from the field, small foundries, large foundries, IDMs, system designers, system integrators, transition partners in May to really kind of, is there a pathway to do a program or concept around this? So really addressing three things. Can we reduce the time, the design cycle time? Can we increase that transition cycle time and open up those access points? And so a whole host of discussions over the summer, really kind of bringing to the genesis of kind of where that concept really comes into play. And so we look forward to additional conversations there to see if there is some concepts there to help really push this concept forward. A couple other things I'll kind of close on, some other interest areas for me in the PNT space. Things we've looked at from the munition side of things is, how do we push that technology even further? Is there a capability in the inertial sensor space to really push to 20 minutes to 30 minute stability? Is there capability there? So revolutionary sensors, error correction techniques, and how do you bring all this together in very small, compact form factors? Something that a lot of interest in at the Army Research Lab over the last handful of years before coming to DARPA was how to do soldier navigation for the dismount warfighter, right? Where I've got 3 to 7 day mission sets. I don't have a lot of, I'm very swap C constrained. What are the solutions there for that space, right? So basically it's very small scale INS. Think about low power, wearable, inertial, as well as aiding sensors to aid that function. How do you then tie this into things like the smartphone that the soldier may already be wearing, right? So we don't want to add extra weight and function. So how do you do that? What are the algorithms to effectively make that compact and efficient? So these are all things we're kind of interested in over the last handful of years. On the case of robotic materials, something that's really kind of interesting for me from the actuation standpoint is how do you bring the coupling of actuation technologies, sensor technologies, low power electronics to really aid those first responders in the battlefield space. And so if we look at, intelligent response to stimuli, integrated sensing and actuation, really bring that to the forefront, especially with sort of the integrated with soft robotic materials. And then lastly, being a materials, with my materials background, a couple things sort of obviously always interested in sort of novel fabrication techniques with MEMS in general, but then how do we leverage some of those newer techniques of atomic layer deposition, additive manufacturing techniques, really to bring in beyond just the simple conductors and insulator materials we commonly see, but how do you bring in functional materials? So your shape memory alloys, your piezoelectric materials, how do you bring that into that capability and then integrate that with our more common process flows and capabilities? And so with that, I'll look forward to any opportunities for discussion, and I'll transition back over to Jay.
Thanks. All right, so we have a little bit of time for questions, so why don't we bring the program managers up. If you have the app, want to ask a question or vote on questions, please do so. I'll be keeping an eye on them. It doesn't matter. All right, so I'll take the first question from the audience. This is a spectrum question, so I'll start with Tim and Tom. We heard yesterday from Wide Bandgap Semiconductors that the Navy was really sort of a driving force that helped sort of pull that technology through for a while. We heard from Stowe about this sort of somewhat grand concept of mosaic warfare and complexity as a tool. You guys are doing a lot of work to enable complexity in RF systems. Is there really an application you have in mind? Is there a specific pull that you see sort of helping get those tools of agility and diversity and intelligence across to the warfighter?
Yeah, I saw the question on the app, and I guess I'll respond specifically for Midas. One of the questions related to some of the study work that was done before the Wide Bandgap Semiconductor program to sort of show why there was a compelling need for more power. In the case of Midas, I mentioned I was coming from Lincoln Laboratory. We had actually done a study at Lincoln to show some of the challenges associated with networking tactical platforms and why there was a compelling need for multi-beam access to do that ad hoc networking. And so that study at Lincoln actually, once again, helped me put together the program. And through working with the services, I was able to understand that this really would be a real need. So we do that type of thing. And so there is some real system pull oftentimes.
And for me, it's the fighting at the tactical edge, thinking about urban warfare and fighting our near peers and peer adversaries, and their ability to deny us the ability to communicate, the ability to use the electromagnetic spectrum for our purposes, or the possibility of them denying that. And I want to both protect our troops and their ability to live and work and not expose themselves in unnecessary ways of information leak and degradation of comms, and then fight them and again do the same to the adversary. So this is really a close-in, near-peer adversary fight at the tactical level that I'm thinking about. Of course, if we get any farther, we go into TTPs, and so we'd have to talk offline about that.
All right, I'll go ahead and address a very practical question, seems to be popular, which is, can people get your PowerPoint slides? I actually don't know if these will be posted on the D6D site or anything. I'd say if you want to just contact PMs directly, if you're interested in their interest in talking to them, they are releasable, so I'm sure they'd be happy to share them. Next question is about transition. It may actually take this question in a little bit of a different direction. Because we are obviously doing this work for the purpose of the warfighter. In electronics in particular, there's always a concern that electronics to get to the warfighter need a commercial pull, and that that commercial capability erodes some advantage that we may get from developing that technology in the first place. So when do you start thinking about that, and how do you sort of balance that trade between having something exist out in the world and having some decided advantage for our side? So, Gordon, sure. Start with you.
Okay. So for sure, for photonics, I think it's important to have a dual-use commercial path that helps to pull the technology. Generally speaking, this stuff becomes much more capable and achievable when there are multiple places to put it. The reason that the DoD needs to be making investments is sort of twofold. One, we want to be the ones that create the innovation, and we want to do it domestically so that we have access to it when it's there, but we also want to have the ability to do differential kinds of things. And so, for instance, MOAB, which is looking at doing LiDAR, there's a clear path to doing autonomous navigation for vehicles. But we can scale that up and make much more exquisite LiDAR that'd be useful in a DoD platform, especially if we own the technology and control how it gets deployed.
And one quick thought on it too is I think it's the number of sensors that we think we need or we want in the field. Tim talked about space fence. We can build one, maybe two of those. But when it comes to the actual sensors for the soldiers, the number that we have to produce drives us to think about the only way to get those costs down is to look at it from a commercial perspective. So if we can trade that off, if we can get the low cost, the many sensors, not having to think about it interface in the commercial world, sure. But right now, I don't think we see that path.
Yeah, Mark Rosker said yesterday at the Wide Bandgap seminar that some niches are big enough, right,
Yep.
that you can fit. Sometimes they're not, and you have to figure out how to get there.
Right.
So Tim, how do you see sort of the balance between 5G and where that's headed versus
Right.
things that might go into Midas?
Yeah, that's a good question. A lot of people brought that up with Midas. What is going on in the 5G market is absolutely the right thing for the commercial market. They are very focused on cost and a standard, right? Initially, they're focused on 28 gigahertz. And so the right thing is a very focused effort on those analog phased arrays. However, we don't have that luxury within the DoD, so we need that wideband frequency agility. And one way to do that is with digital arrays, which is why I would say that there is a distinction there between the two. But of course, we'll leverage what we can when appropriate. But mostly, we'd be leveraging some of the semiconductor processing. I think leveraging the advanced CMOS as the core there is important. But Midas really is solving a different problem. I sort of joke that 5G will provide you, internet access to your Starbucks, but that's very different than trying to get two F-35s to talk to each other at 100 nautical miles, right?
Yeah, let's also not forget that standards are meant to be discovered, intercepted, and they're fairly easy to geolocate. All things that we don't really necessarily want for our purposes.
All right, so I think I have time for one more. I'll ask this one myself. So we talked at the beginning about sort of the electronics focus, the ERI. We'll hear about that one tomorrow. I'd also just point out to people that's a very artificial division in the office. Tom, in fact, is managing ERI programs, so this is probably a softball for you. But really, processing digital information really is pervasive across a lot of what we do. So any thoughts about how advanced processing may impact your fields, or even thoughts for people who may be proposing to you how they might want to think about things at the boundary of advanced processing, what we're doing with ERI, and how they would impact your programs?
I'll take a stab. So, and these atomic sensors, they get more and more complicated. They become basically a huge escalation of many parallelized feedback loops. And it's getting to the point for these very sophisticated systems that you do need to digitize all these signals and have high speed, high performance feedback loops all in parallel. So that's a little bit about A to Ds and DDS on one side or the other, but you need fast electronics in between to compute all of that. So I do see eventually needing low power, high performance computing for those applications.
Yeah, I would also kind of follow that up with saying, if you're computing at the edge with the sensors, right? And obviously, I want to make movable sensors, right? And so again, how do you leverage that capability, bring that into the fold, How do you bring that into fold with the correct packaging aspects to really push that together? And in the inertial sensor space, right? If you start to look at what the calibration algorithms that are needed, and all the different coefficients, how do you deal with that in small form factors? Especially if I want to really reduce the weight for adding INS for the dismounted warfighter.
Any other final thoughts?
I would add, digital beamforming. This probably affects both Tom and I. I specifically avoided this topic completely in Midas, that we're really going to focus on that aperture going from the antenna back through the digital data stream. But there's clearly a problem if you have an element level digital array, what you do with that data. We can simply do analog-like functions where we sum signals together. Implementing that is fairly straightforward, and you can have a few beams. But if I want to do full-on MIMO or sort of eigenmode beamforming, where I'm doing QR decompositions on the fly across thousands of elements, that architecture is by no means clear how to implement that. That is a computer architecture and a networking problem. That's not going to be solved at all under Midas. Tom touches on some of it in some of his programs, but it is a problem.
Yep.
And I would say from the photonics side, it's, photonics is better when it is intimately integrated with electronics and vice versa, right? So photonics makes compute better when it's integrated close. And you often need to integrate microelectronics really close to the device when you're trying to make better photonics. So, they're really close together.
All right. I think we are out of time. Again, thank you very much for spending some time with us, and hope to see a lot of you back tomorrow morning.